Hello, everyone, and thank you for watching this presentation. I am Kyropoulou with HKS Architects and the University of Houston, and I'm here with my colleague Saurabh Shrestha with Dialogue Architects based in Toronto. Today, we are presenting the early design development from the standpoint of building performance of a low source energy passive design for the new neonatal unit that is part of the referral hospital in Mbale, a remote small town in Uganda in Eastern Africa. We will outline several challenges and the way we decided to overcome them, and we will go through the evaluation methodology for the building strategies. In the end, we will show how this design is aiming to help reducing the neonatal mortality rate to the lowest possible level within the region and beyond, by designing the neonatal facility in a way that is sensibly addressing the significant challenges of low resource settings while also serving as a model for other low resource settings. The goal of this project is to design a self-sustaining net zero building. Today, the unit is operating from one single space that was initially designed for 10 patients with their mothers and is in practice hosting an average of 55 patients at a time. Instead of bassinets being at the feet of the mother's beds, neonates are arranged next to each other on the beds, and the mothers are sitting or standing. Understanding the localities of the project included, of course, understanding the climate and its effect on building design. The Köppen-Geiger classification indicates an AM tropical monsoon climate. It is influenced by its proximity to the equator with high solar radiation and its position to at the foot of Mount Elgin. The climate is warm and humid without extremes, and there is hardly any seasonal variation in temperature throughout the year. Humidity is steadily it steadily remains high, and there is a clear rainy and dry season. If no upper limit is set on humidity, something that is both culturally accepted and also follows comfort in naturally ventilated spaces, thermal mass and night ventilation are an effective combination that, in conjunction with internal gas dissipation, can extend the comfort band sufficiently to cover all temperatures year-round. The basic environmental principles are divided between those that contribute to thermal performance, daylight, water management, and energy generation. Several architectural strategies, mostly around massing and facade treatment, sometimes synergistically and other times individually, contribute to several phenomena that then support the four individual pillars. The building general massing is developed around the extremely low nurse to patient ratio, which is 2 nurses for 50 neonates, which drove the evolution of the design around the central nurse station, serving mainly good visibility and security. There are 2 structural grids, one along the east-west axis and one that follows the current campus. The development of the design led to a double roof system that unified the design. The main work area, as seen in the far right image, is an open space that was used as an indication for early design decision-making. I'll now pass it to Saurabh that will go through the building performance analysis in a little more detail.
Thanks, Millie. So most beds are arranged due north-south with overhangs designed per latitude angles to cover all direct sun exposure. The initial simulated evaluation started with daylight assessment. Different window sizes and configurations were tested in a parametric way, and the vertically elongated shape was proven to be the most effective. The simulated study we see here shows useful daylight illuminance distribution in the space after implementing all optimization strategies. Besides the shaded windows configuration, the most decisive strategy is the centrally located shaded clerestory along the core that brings substantial indirect illumination to the center. This operable clerestory is also a key strategy for natural ventilation. The initial central deeper area only relied on cross ventilation and was proven to be low in air changes per hour CFD analysis, shown in the graph in red. The addition of the clerestory contributed to rapid increase of air changes per hour, shown in blue in the graph, exceeding ASHRAE recommendations. with a wind speed close to the measured average maximum, the CFD analysis indicates a significant increase in air changes per hour. This becomes even more apparent with lower wind speeds that are reportedly a common case in the region. We see an increase from practically 0 to about 2 air changes per hour. Thermal mass is one additional core strategy that helps minimize fluctuations throughout the day. The temperature fluctuations during the day are flattened by about 3.5 degrees total. Daily temperatures seen as black line when thermal mass is applied against the red line that is without thermal mass. Annually, thermal mass adds additional 10% of time where natural ventilation can be an effective strategy. To understand the simulated earlier design annual model of the ward space, we use the adaptive comfort band for naturally ventilated buildings between 18 and 28 degrees Celsius. It's worth noting that higher temperatures may be tolerable, especially in the present design where thermal regulation of premature neonates is achieved with clothing and kangaroo baby carrying by the mother. The simulated space shows that lowest temperatures never fall under 20 degrees Celsius, and although higher temperatures are common, they never exceed 28 degrees Celsius. Whole building thermal modeling is showing year-round temperatures well within comfort. To achieve net zero and be able to provide power during critical moments of frequent power outages, an array of photovoltaic panels is designed on roughly half the roof of the central building, with estimated energy output at 75 kilowatt hours a day, a capacity able to cover for all energy demand of the daily average uses. One complementary strategy is also water harvesting, that is acting as an additional source of resilience that supports mainly hygienic habits and medical procedures. For the most vulnerable human beings in the world, we are looking forward to creating a net zero space that will serve as a potential for a model for other low resource settings. Of course, there are a lot of components that relate to medical planning and operations that this paper did not have room for, but we're open to any questions that you may have during this session. The creators of this project worked pro bono and its implementation is dependent on donations. Thank you very much.